Hello everybody, welcome to the course VLSI Design Flow RTL to GDS. This is the 32nd lecture. In this lecture, we will be discussing scan design flow. Specifically, in this lecture, we will be discussing the design modifications that are required to implement scan design flow, the mechanism of testing during scan design flow, and the tasks that are required to be done to implement scan design flow. Now, first let us look into the design modifications that are needed to implement scan design flow. So, in this circuit we are showing a schematic of the original circuit. So, this is the original netlist or original design, and this original design is basically being transformed to another design in which the scan design flow is implemented. So, what are the changes required to be made in this new design or new circuit, right. So, there are three major modifications that needs to be done over the original circuit. The first modification is to add extra ports. So, we add extra port, that is TM or test mode, the scan enable or SE, and the scan in and scan out. So, these 4 extra ports are added to the design, right. And then what is the second modification? The second modification is to change all the or replace all the D flip flops that are in there in our design with a scan cell. Okay. So, what are scan cell? We will see. Okay. So, we replace D flip flops in our design with another kind of memory elements which are known as scan cells, and then we connect these scan cells in such that a shift register is formed, right. A shift register from the input port to the output port is formed using this scan cells, and once we connect and make this a shift register, this shift register is also known as scan chain. Okay. So, because this is a chain of scan cells, and therefore, it is known as scan chain. Now, what do we gain out of these modifications? Why do we do these modifications? So, these changes dramatically improves the controllability and observability of memory elements, that is flip flops, in a sequential circuit. So, in the last lecture we had seen that to apply test patterns at the internal components of our design and observe the effect of the fault from the internal elements to the output port, we need to make our circuit controllable and observable, and this problem is much more complicated for sequential circuit, in which we need where the state elements are involved, and we need to traverse the states in the FSM to reach to apply some test pattern or to observe the responses. So, for the sequential circuit, doing this kind of modifications improves the controllability and observability drastically, and how does it improve? We will see in the subsequent slides. Okay. Now, these are three major changes or modifications that are done in a design to implement scan design flow. First, to add the port, the second, replacement of the D flip flops with the scan cells, and then connecting them to form the scan chains, right. So, now we will look into all these three modifications in more detail. Now, a scan design works in different modes, and what are these different modes? So, there are three modes. The first one is the normal mode. Normal mode meaning that we are doing the normal operation of our circuit, it is delivering the required functionality, right. If we consider that there was an original netlist, which were delivering some functionality. So, the normal mode will deliver the same functionality, right. So, the normal functional mode of our chip, that is the normal mode. Then in addition to normal mode, we have a shift mode, and in shift mode what happens is that memory elements work as shift registers. So, by making changes in our design, we have transformed or replaced all the cells, all the memory elements with scan cells, right, and then made a shift register or scan chain of using these scan cells, right. Now, in the shift mode, these memory elements or these scan cells work as shift registers, right, and using these shift registers, we are able to shift in the required test pattern into our circuit, and also using this shift register we can detect, we can read the value of any internal net in our circuit at the output port, right. So, we when the circuit goes into scan mode, then what happens is that the flip flops or the scan cells, those are connected in the form of shift register, and using this shift register will be transferring in the test pattern to, at the internal nets of our design, and also reading the values of the internal nets at the output port. And the third mode is the capture mode. Now, what is the capture mode? In capture mode, the response of the fabricated circuit is captured during testing, right. It is, so capture mode is effective only in the test mode, while we are doing a testing of our circuit, right. So, when our circuit is, we are doing a we are testing our circuit after doing manufacturing, and during that testing phase, or during the testing of our chip, where if we want to read the response of the fabricated circuit for the nets and internal and the signals in our design, then we take our circuit to the capture mode, right. Now, these three modes of the of our circuit can be defined with the help of the values at the input ports, right. Now, what are these values? So, if the circuit is operating in normal mode, that is, we are carrying out the chip is out of the environment of testing, that means it is this is working in our system where it should be, or it is in the field. At that time, whenever the chip is delivering the normal function, at that time we make test mode as 0, right. We make the signal test mode or test port as 0. So, it implies that our circuit is not being tested, it is delivering the normal functionality. When we want to test, that is in the manufacturing environment, when we have fabricated our die and we are trying to test our IC whether it is working or not, working properly or not, then in that case we take test mode to 1, right. We make the signal test mode is equal to 1, meaning that now we are testing our chip, right. And in the test mode, there while we are testing, there are two modes. The first one is shift mode and the other is the capture mode. Now, in the shift mode, what we do is that we make the input port scan enable SE as 1, and in the capture mode we make scan enable as 0, right. So, with the help of these input ports TM and SE, we are able to define 3 different modes of our circuit, and these modes will be useful while we are doing the testing in a scan design flow. Now, what are scan cells, right? We said that we replace each flip flop in our design or D flip flop in our design with scan cells. Now, what are these scan cells? So, there can be many different kinds of implementation of the scan cells. One of the most popular is mixed D scan cell. So, let us look into the internal detail of or internal implementation of mixed D scan cell. In mixed D scan cell, we will have a multiplexer. We will have a multiplexer, 2 to 1 multiplexer, and it will be basically having extra pins. So, what are these extra pins? So, the first, the D pin, the clock pin and the Q pin are similar to a traditional D flip-flop, right. So, we have D flip-flop in which we have say clock pin, we have D pin and we have Q pin, right. So, these 3 pins are similar to it. So, this is the figure of Mux-D scan cell. So, in this Mux-D scan cell, these 3 pins are similar to the D flip-flop. However, it has got extra pins Si and Se. So, Si stands for scan input and Se stands for scan enable, right. Now, what is the functionality of this scan cell? So, the multiplexer basically selects data between D and the Si using the scan enable pin, right. So, now what happens is that if scan enable is equal to 0, then this path will be active and this flip flop will latch whatever was there at the D input, right. So, basically when scan enable is equal to 0, this scan cell is working as a normal flip flop, right. Whatever is at the D, it will be getting captured when the positive clock edge appears at the clock pin, right. That will appear at the Q pin, right. And in the however, when we make scan enable as 1, right, when we make scan enable as 1, so in that case what happens, the value not from D but from Si pin, that will be actually going to D and that will be getting latched, right. So, in the value at Si input will be latched. So, the output pin, the Q pin here will be produce the content of the D flip flop, right. So, the next state, whenever the clock edge comes, the flip flop, the scan cell goes into the next state and the next state will be either the value of D or the value at the Si input. When will the value of D be captured? When Se or the scan enable is equal to 0, and when will the value at Si be captured? When the scan enable is equal to 1. Now, how do we form the form scan chain in our design? Okay. So, let us take an example. Suppose we have our design like this and in which there are say 3 flip flops F1, F2 and F3, right. Now, we want to make modifications in our circuit to allow it to do the testing or scan, or we want to implement scan design flow in this circuit. So, what circuit modifications we will be doing? Okay. So, this is the modified one, right. So, this is the original circuit and this is the modified, right. Now, what modifications we have done? The first thing we should note is that we have replaced all the flip flops, all the D flip flops with scan cells, right. So, F1 is now a scan cell, it is not a D flip flop, right. It is scan cell and scan cell. These are the circuit change. The first circuit change is that all the D flip flops have been replaced by scan cells, right. And then the Q pin of the scan cell and the D pin, and the D pin of the scan cell and the clock pin of the scan cell, those connections are not changed, those are made as original. So, the nets for which the original connection is preserved, those are shown by this dashed line. So, these are dashed line for these nets, no changes have been made in the modified net list or modified circuit. So, if we see the D pin of the scan cell, it is as connected to the previous case. Similarly, the D pin of this scan cell and the D pin. Similarly, if we consider the clock pins, those connections are not changed, those are same as it was earlier, right. However, for the Q pin also the original connections are preserved, right, but some extra connections are made. What are those extra connections? We will just see. Now, the Si pin of the first scan cell is connected to the Si port. Now, we have also added extra ports Si and Se. Si is scan input and Se is scan enable, right. Now, from the scan input port that we created, we take a net or wire and connect it to the SI input pin of the scan cell, the first one. So, SI pin of the first scan cell is connected to the SI port. This connection is made. Okay. Then what is done? The QSO pin of one cell is connected to the SI pin of the next cell to form a chain. So, the Q pin of this scan cell is connected to the next scan input pin of the next cell. So, this connection is made extra, right, from here to here to here, this, right, this extra connection is made. Then again from this flip flop, this scan cell, the Q pin is taken out and it goes to the scan in pin of the next flip flop or scan cell, right. And finally, what happens, the last one, so in this case there were only 3 flip flops, so there are only three the connections from a Q to SI of the, so to SI pin of the next flip flop and so on. If there were say 10 flip flops in our design, so we would have connected first to the second to the third to the fourth and so on, and would have formed a chain of 10 flip flops or 10 scan cells, right. So, here there are only 3. So, we have in the chain we have only 3 flip scan cells, right. Finally, what we do is that the one which is at the last, right, from there we take the pin, connection from the Q pin and take it and make it to the SO port, right. So, now after we have made this change or made the connection, made a scan chain, now there is the path from SI, that is scan input, to the first scan cell, right, and then to the second scan cell, then to the third scan cell, and finally from scan cell to the output. So, from the scan input to scan output, we have a shift register, right. Now, when will this shift register be active? When we make scan enable is equal to 1, right. So, what we do is that we connect all the scan enable pin of the scan cells. So, this is the scan enable pin of the first, second and third. We connect all of them to the scan enable port that we have created. Now, whenever this scan enable port is equal to 1, then the whatever we put the value at SI port, that will be captured by the next flip flop and the next flip flop and so on in different clock cycles. So, as the new clock cycles clock edges come, the data from the input SI port get transferred to the to this scan chain all the way up to the SO port, right. So, we form a scan chain consisting of n cells. In this case, there are only 3, therefore, there are 3 cells in the scan chain, right. Any test vector can be shifted in from SI port in n clock cycles, right. Suppose for example, the initial value of all these flip flops were 0. Let us assume that the Q was 0, 0, 0. Now, if we want to make all of them as 1, 1, 1, how many clock cycles we will require? So, we will apply a sequence of 1, 1, 1 at the scan input, right, and make scan enable is equal to 1, right, and allow the clock to trigger all these flip flops, right. So, in the first clock cycle, this will get 1, right. In the next clock cycle, this one will go to the next flip flop and the other one will come to this, right. And in the third clock cycle, this one will go to the next flip flop, this one will go to this flip flop or scan cell, and the final one will come here, right. So, in 3 clock cycle, we will be getting any test vector we want at this at the output of this scan cells, right. So, any test response can be shifted out to SO port in n clock cycle. As we have shifted the input pattern into our circuit, similarly whatever the response that will be received at the D pin, that can be transferred to the SO port in maximum n clock cycle, right. So, without a scan chain, it could have taken exponential number of cycles, right. For example, suppose these flip flops were part of a counter, right. If these flip flops were a part of the counter, and if the initial state was 0 0 0 and we wanted to get 1 1 1, right, then how many clock cycles would have required, right, 2 to the power, in that case we would have required 2 to the power 3 or around 8 clock cycles, right. So, instead of exponential number of clock cycle, what we will be requiring will be the linear number of, or number of clock cycles will be related to number of scan cells, linearly related to number of scan cells in the scan chain. So, in this case there are 3 cells in the scan chain. So, in maximum 3 clock cycle we will be getting any value at this scans at the Q of pin of this scan cell, and also will be able to read any value at the D pin at in 3 clock cycle maximum, right. So, this is how the scan by making scan chain in our design, how we simplify the writing of test vectors into our internal nets of our design and reading the value from the internal nets of our design. Now, after we have done scan cell insertion in our design, the pins of the flip flops, meaning the D pins and the Q pins, have become easily controllable and observable from the primary input, meaning the primary input in this case SI input port and the scan enable, right. Now, once we have done the scan cell insertion, we can treat the Q pin as pseudo primary inputs. Why we can treat the Q pin as pseudo primary input? We can treat them as pseudo primary input because if we want to write any value at the Q pin, or we want to get any value at the Q pin, for example 0 or 1 at this point, we can do that, we can obtain that with the help of the scan input port, right. We apply proper value, appropriate value as scan input port, make scan enable as 1 and allow the clock to propagate, and we will obtain 0 or 1 at this point, right. So, in effect these Q pins which can be used to deliver any, it can be used to deliver any value 0 or 1 to the combinational circuit elements in its fan out, and therefore, we treat the Q pin of the scan cell as pseudo primary input after scan cell insertion. Similarly, if whatever the value that is obtained at the D pin, right, that can be propagated to the output port SO in linear number of clock cycles, and therefore, the D pin can be similar, can act similar to the pseudo primary output, right, because the D pin can be considered as an observability point, right, it can be directly observable, and whatever the value is observed at D pin, that can be propagated through the scan chain up to the scan output port, and the value at the D pin can be easily observed, and therefore, we can treat D pin as pseudo primary output for our sequential circuit after scan cell insertion. So, how does this scan cell design ease the testing? So, it effectively transforms the problem of sequential circuit testing to combinational circuit testing. So, after we have done scan cell insertion, we can assume that whatever the value we want, we will get at the Q pin, right, because those are pseudo primary inputs, and whatever the value is at the D pin of the flip scan cell, we can easily observe at the output, and therefore, those are pseudo primary inputs. So, now we need to only worry about the combinational circuit elements between these scan cells, right, and therefore, the scan design scan insertion or transforming or making transformations for scan design flow, it effectively transforms the problem of sequential circuit testing to combinational circuit testing. And the automatic test pattern generation, the ATPG problem effectively changes from sequential to combinational, right. Now, what the ATPG tool or the automatic test pattern generation tool, they need to just worry about that what patterns will be required to test the combinational circuit element in the design. Why? Because combinational circuit element will be either be driven by the input port or the scan cells. So, the scan in the scan cells, the output will be obtained from the Q pin, and Q pins are pseudo primary inputs, meaning that we can apply any pattern at the Q pin with the help of the scan chain, and therefore the testing becomes very easy, or the testing problem becomes very easy, and the and generation of the test pattern for the ATPG tool becomes much easy because of scan cell insertion. Now, what is the mechanism of, like, how do we proceed in doing testing for a scan inserted design? So, at the time of testing, say we have manufactured our die, right. Now, we want to do the testing. Now, what should be done during testing for a design in which we have made the changes as described earlier, right. So, first what we do is that we go into the shift mode, right. So, we studied that, or we discussed that when to go into the shift mode, we make scan enable is equal to 1, right. So, we make scan enable is equal to 1, shift in the desired test pattern using ports Si to the scan cells F1, F2, F3, right. For example, now we will shift in the required test vector. For example, if we want, say, 1, 0, 1, whatever. So, we will apply 1, 0, 1 here at the scan input, and then allow it to propagate through the scan chain, and then we will get this values at the Q pins of the scan cell. Now, then we apply the required test pattern at the input port also, right. Now, in suppose we want to test this AND gate, right. So, suppose we wanted to have a test pattern of 1, 1 to test this AND gate. So, for that we will need to make Q is equal to 1 and also C is equal to 1, right. So, that is why we said that we apply the required test pattern at the input port also, right. So, we shift the value shift the required test pattern to through the scan input to the scan cells in our design, and also we apply the appropriate values at the other input ports. So, in this case A, B, C, D, E, right. And once we have done that, then all the required test pattern is loaded into our design, right. Now, once we have meaning that we have applied the test vector that we needed to apply in our design, right. Then what we do is that we go into the capture mode, right. Now, in the capture mode we set scan enable is equal to 0. For one clock cycle, we make scan enable is equal to 0. Now, what happens in that case is that, suppose we want there was a stuck at 0 at this point, and we had loaded 1, 1 pattern at this point, or we had applied this pattern during the shift mode, right. Now, we want that the correct value, or the correct value for this AND gate is that its output should produce 1. Now, for a faulty circuit, if there was a stuck at 0 fault at this output pin, right, then instead of 1 we will get 0, right, and that 0 will come where? At the D pin, right. Now, for one clock cycle, when we make scan enable is equal to 0, then remember that we had in the scan cell, we had a multiplexer, right. We had a multiplexer, and if scan enable was equal to 0, then whatever was D, that was being captured by the flip flop, and that appeared at Q, right. So, when we make scan enable equal to 0, scan enable is equal to 0, the D value, that is 0, will be read and that will appear at Q, right. And then what we do is that, if there was a fault for which the test vector was applied, scan cell will now capture the result of the fault and receive the faulted output, right. So, in this case the faulted output is 0 instead of 1, that was the correct, there was a stuck at 0 fault at the at this AND gate. So, the Q pin will have a value of will have a value of 0, right. And then what we do is that we again go to the shift mode, right, and then switch back to the shift mode and make this scan enable is equal to 1, scan enable is equal to 1. Now, once we do that, what happens that this 0 goes through the scan cells or and through the scan chain, and it will get appear at the output port SO in maximum n clock cycle, where n is the length of the scans, right. So, we switch back to the shift mode, so shift out the captured result to the SO port. So, whatever was captured by the D pin, that or what was captured during the capture mode, that will appear at the SO port after a delay of maximum n clock cycle, and we can read the values that we are obtaining at SO port. If we get, instead of 1, we get 0, right, we can infer that there was a stuck at 0 fault at the input at the AND gate, right. So, this is how we can detect the fault, right, and the result is compared with the expected response, and if they mismatch, we infer that there is a manufacturing defect or there is a fault. So, when we are doing this shift mode, right, so we started with shift mode, we went to the capture mode. Then when we are doing the shift mode, we also apply the next test pattern. Suppose in the first test pattern was 1 1 1, right, 1 1 1, and the next pattern was say 1 0 1. So, now we will apply 1 0 1. So, while we are shifting out the computed result through the scan chain, we are also passing in the next test vector, right. So, the sequence of shift, capture, shift, capture, shift, capture will be repeated as many times as there are number of test pattern. For example, if there are 1000 test pattern, then this has to be repeated 1000 times, right. And if for any test pattern there is a fault and we observe a different value at SO as than what we are expecting, we infer that our chip is bad, and then we do not ship that or take that chip to the next stage, right. Now, what task do we need to perform in scan design flow? So, first we need to prepare our design, right. So, we need to pick so that the design become testable, right. Now, while even writing the RTL, we should be very careful that whether our design is testable or not, right. So, there are tools available which help us understand that if there are any issues in the RTL or are in our design which will create problem later in the implementation of the scan design flow, then those tools will flag violation, and then we need to fix those violations. For example, suppose we have a circuit, right, and there is an FSM, there is an internal FSM, and it is generating say reset signal, right, and this is asynchronous reset is going to our flip flop, right. This asynchronous reset is going to our flip flop, and we have actually converted this flip flop to scan cell, right. Now, if we have done that, and during this testing, this reset signal gets asserted somehow, then the scan chain will be broken and our scan design methodology will fail, right. And therefore, we while implementing scan design methodology, we should be careful that the internally generated reset should be deasserted during the scan mode, right, or during the shift mode, right. So, this is just an example of one of the guidelines. There are other guidelines which needs to be taken care of while designing or while making our design or implementing the scan design methodology in our design. So, these things must be taken care of during the earlier stages of our design implementation while writing the RTL and so on, right. Now, later on when we have the netlist, we do scan synthesis, right. So, in scan synthesis, design becomes scan design. So, we are inserting features or making design modifications to implement the scan design methodology, right. So, in this, first what we need to do is that we need to define scan configuration, meaning how many scan chains we want in our design. So, if we keep one very long scan chain in our design, then it may take a long time to test and load the pattern, right. And therefore, we can partition these scan chains into smaller scan chains. And how many such scan chain will we want in our design, that we can give as a parameter to the tool that is implementing the scan synthesis as a configuration parameter, right. Then we need to say that which scan cells need to be picked from the library. So, the scan cells are designed and they are actually modeled and kept in the technology libraries. Now in a technology library, there may be say 10 different types of scan cells. Now, we may not want, we may want to use only say a few types of scan cells. Then we can give instruction to the tool that which scan cells we need to use in our design. And then we can exclude certain elements from being converted to the scan cells. For example, if there is a register or flip flop which is in a critical path and we do not want to change it or or replace it with a scan cell, then we can tell to the tool that okay, for this particular cell do not do scan replacement, right. So, those kind of configuration needs to be defined while in doing scan synthesis or doing scan cell insertion, right. And then during synthesis, we need to replace these flip flops with scan cells that we have already seen, right. And then there are some tasks related to scan design flow which is needs to be done in physical design, and these are scan reordering and stitching. So, what are these tasks? We will be discussing when we will be discussing physical design. Now, and during this after we have done physical design and we have reordered our the scan cell, then we can do test vector generation or to generate the test patterns that will be used to test our chip. And we also do some verification or we carry out some verification tasks to ensure the sanity of our scan chain, the timing verification and other things. For example, once we do scan cell insertion, then there are very many there is a shift register kind of structure, right. You have a Q pin of one scan cell and it is going to the SI pin of the next scan cell, and there are no circuit elements between them, right. And if the data path is very small, then we have studied during in the STA that there can be hold violation, right. So, we have to verify timing and be careful of the hold violation. So, these types of checking or hold violation checks are typically done after we have done say clock tree insertion, because once we get the clock tree, then we have a fair idea of hold violations, right. And we also do some sanity checking of the scan chains using logic simulators, that whether we are whatever the value we are applying at the scan input port, whether it is being propagated properly and so on. And we also need to ensure using say combinational equivalence checking that after scan cell insertion, whether our design is functionally equivalent to the earlier original design in the functional mode or in the normal mode, right. That if there was some problem in this scan cell insertion, then those problems will be caught, right. So, we carry out combinational equivalence checking to make those to ensure those things that the functionality of our chip has not broken. Now, we have seen that there are lots of advantages of scan design flow in improving the testability of our design. But what are the costs involved in this, right? So, the first cost is related to the area overhead. The area overhead will be because of the larger scan cells and also the routing resources required for routing say scan enable signal and then making the scan chains and so on, right. And then there are costs involved related to the extra input and output ports that we create for implementing scan design flow. And then there is a degradation, there can be degradation in timing in scan design flow. Why there can be degradation in timing? It can happen because there is an extra multiplexer within the scan cell, right. So, if we see the scan cell, right, there is an extra multiplexer, and the output of the multiplexer goes to the D pin of the internal flip flop, right. So, if we consider the data path, in the data path when scan enable is equal to 0, in that case in the data path we have extra multiplexer, and that will add to the delay on the data path, and therefore, the maximum clock frequency at which our circuit can operate, that can come down. And then there is significant effort from or design effort to implement scan design flow, right. Now, these are some of the important costs that we must be considering while implementing scan design methodology. Now, despite this cost, the scan design methodology is quite popular for industrial designs because it improves the testability of our design significantly. Now, if you want to go deeper into the topics that we have discussed, you can refer to these books. And just to summarize what we have done in or what we have covered in this lecture, we have looked into that what design changes we need to make to implement scan design flow, and what is the mechanics of scan design testing, and what are the design tasks that we need to carry out to implement scan design flow. So, in the next lecture, we will be looking at how we can generate the test patterns to test our chips. Thank you very much.